Picture this: a universe so young it barely has stars, a vast black canvas shimmering with the faint glow of newborn atoms. But then, something impossible happens. Against all odds, simple particles begin to link together, forming the very first complex molecules in existence. How? That's one of the greatest unsolved mysteries of our cosmos. We're talking about the moment when raw ingredients of the universe, hydrogen, helium, and traces of heavier elements, somehow defied the chaos of deep space and assembled into structures intricate enough to pave the way for everything that followed. This isn't just chemistry, it's the origin story of complexity itself. Today, we're diving into 30 breathtaking theories that attempt to crack this cosmic code, each one a glimpse into the ingenuity of nature, or perhaps something even more extraordinary. Think about how fragile those first molecular bonds must have been, born in an environment where radiation tore through space and temperatures swung violently between extremes. Yet here we are, living proof that they not only formed but thrived, setting the stage for planets, oceans, and life. It's humbling we're made of stardust, but also of those pioneering molecules that dared to exist when the universe was still figuring itself out. What forces guided them? Was it sheer chance, the hidden laws of physics playing out, or something we haven't even considered yet? The answers might rewrite our understanding of reality. This journey won't just take us back in time, it'll stretch our imaginations. Some theories suggest cosmic rays acted as cosmic matchmakers, zipping through clouds of gas and sparking chemical reactions. Others propose that dust grains in space served as microscopic laboratories, shielding delicate molecules until they grew sturdy enough to survive. And then there are the wild cards, ideas so bold they sound like science fiction, like molecules forming in the hearts of collapsing stars or even riding the shockwaves of supernova. Every possibility opens a new door, and behind each one lies a universe of wonder waiting to be explored. So settle in, because by the time we're done, you'll never look at the night sky the same way again. Let's start with one of the most enduring ideas, the primordial soup hypothesis. Imagine Earth billions of years ago, a volatile world with lightning cracking through thick clouds, volcanoes belching gases into the air, and vast oceans simmering under a young sun. In this chaotic environment, simple molecules like water, methane, and ammonia mingled freely. The theory suggests that these basic ingredients, energized by lightning or ultraviolet light, began linking up in the shallow waters, forming amino acids, the building blocks of proteins and eventually life itself. It's a poetic image, life's first sparks flickering in tide pools under stormy skies. This idea gained legendary status thanks to the groundbreaking Miller-Urey experiment in the 1950s. Scientists Stanley Miller and Harold Urey recreated Earth's early conditions in a lab, mixing water with gases thought to exist in the ancient atmosphere. Then they zapped it with electricity, mimicking lightning. Within days, the mixture turned pink, a sign that simple molecules were combining into more complex ones, including amino acids. It was a revelation, showing that the leap from chemistry to biology might not require magic, just the right conditions. But here's the catch: this theory has a blind spot when it comes to the broader universe. While it beautifully explains how complex molecules could arise on Earth, it doesn't account for the fact that these molecules exist everywhere. Astronomers have detected amino acids in meteorites and even floating in the vast clouds of deep space. If Earth's oceans were the only kitchen where these molecules cooked up, how did they end up scattered across the cosmos? Some scientists argue that the primordial soup might have been a universal recipe, with similar chemical reactions happening on icy moons or in interstellar clouds. Others think Earth's version was just one of many experiments the universe ran. There's another twist: the early atmosphere might not have had the exact mix of gases Miller and Urey used. Recent studies suggest our planet's ancient air could have been less reactive, making lightning-triggered reactions rarer than once thought. Does that mean the soup was more of a niche dish rather than the universe's main course? It's a humbling reminder that even the most elegant theories need to adapt as we learn more. So while the primordial soup hypothesis remains a cornerstone of origins research, it's clear the story doesn't end there. It's like discovering the first chapter of a cosmic mystery, one where Earth's oceans were just a single paragraph in a much grander narrative. The search for answers pushes scientists to look beyond our planet to asteroids, distant nebulae, and even the hearts of dying stars, asking, if life's ingredients are universal, what else is out there waiting to be stirred into the mix? Now let's dive into the depths literally, where sunlight never reaches and the pressure could crush submarines like tin cans. Hydrothermal vents, those towering chimneys on the ocean floor spewing superheated, mineral-rich water, might seem like the last place you'd expect life's building blocks to assemble. But these extreme environments have something the primordial soup lacked: a relentless, energy-rich chaos that could have jump-started molecular complexity in ways we're only beginning to understand. Picture a vent gushing water heated to over 700 degrees Fahrenheit, loaded with dissolved metals and sulfur. Around it, a gradient forms scalding at the center, cooler just a few feet away. This creates a natural laboratory where molecules are constantly pushed, pulled, and rearranged by the shifting conditions. The vent's porous rock structures act like microscopic factories, with countless nooks and crannies where simple compounds could concentrate and react. And here's the kicker: the minerals spewing from these vents, like iron-sulfur clusters, are eerily similar to the ones our own cells use to process energy today. It's as if life's earliest chemistry left clues buried in the geology. One compelling piece of evidence comes from lab simulations. Scientists recreated vent conditions by mixing water with minerals like pyrite and subjecting it to heat and pressure. Remarkably, they observed simple carbon-based molecules linking up into more complex chains, some even resembling the precursors to fats and proteins. Unlike the lightning-driven reactions of the primordial soup, this process doesn't rely on a lucky strike. The vents provide a steady, sustainable energy source, like a slow cooker for molecular evolution. But the real magic might lie in the vent's chemistry. The alkaline fluids bubbling up from below interact with the acidic seawater, creating a natural proton gradient, a miniature version of the energy-generating process modern cells use. Some researchers think this gradient could have acted as a primitive battery, driving reactions that turned simple molecules into something far more intricate. It's a tantalizing idea. Life's first sparks might have flickered not in sunlit ponds, but in the dark, pressurized fractures of Earth's crust. Critics point out that hydrothermal vents are volatile, constantly erupting, collapsing, and shifting. Could delicate molecular structures survive such turbulence? Surprisingly, yes. The same minerals that make vents chaotic also act as scaffolds, protecting fragile molecules long enough for them to stabilize. And vents aren't isolated. They're part of vast networks, meaning successful molecular experiments in one vent could spread to others, carried by circulating water. What's even more mind-bending is that vents aren't unique to Earth. Jupiter's moon Europa and Saturn's Enceladus likely have hydrothermal activity beneath their icy shells, meaning this recipe for complexity could be simmering across the solar system and beyond. If that's true, the story of life's origins might be less about a single lucky break and more about the universe's stubborn habit of building complexity wherever it finds the right ingredients. So while the primordial soup gives us a poetic vision of life's beginnings, hydrothermal vents offer something grittier, a tale of resilience where molecules clawed their way into existence against crushing odds. It's a reminder that life, even in its simplest forms, might thrive where we least expect it, not just in the light, but in the deep, dark, and dazzlingly harsh corners of the cosmos. What if Earth wasn't the kitchen where life's ingredients first cooked, but just the dinner table where they were served? That's the radical premise of panspermia, the theory that complex molecules, or even life itself, hitched a ride to our planet aboard asteroids, comets, or cosmic dust. Imagine a meteorite forged in the fires of a distant star system, carrying within it the blueprints for biology. When it crashed into Earth billions of years ago, it might have been less like a random space rock and more like a delivery truck packed with molecular treasure. The evidence for this idea isn't just speculative. In 1969, the Murchison meteorite streaked across the Australian sky, scattering fragments loaded with over 90 different amino acids, some of the same ones found in our DNA. Even more tantalizing, some of these molecules had a slight preference for one molecular orientation over another, mirroring the bias seen in Earth's lifeforms. It's as if the universe has a subtle preference for certain building blocks, and it's been shipping them across galaxies for eons. But here's where the debate ignites. Does panspermia solve the mystery of life's origins, or just kick it down the cosmic road? If amino acids came from space, where did they form? Some scientists point to nebulae, those vast clouds of gas and dust where ultraviolet light and cosmic rays could have zapped simple molecules into more complex arrangements. Others suggest that ancient comets packed with ice and organic compounds acted as icy factories, their interiors churning out intricate chemistry as they drifted between stars. There's a wilder twist to the notion that life didn't just spread passively but was engineered. The idea of directed panspermia, championed by Nobel laureate Francis Crick, proposes that advanced civilizations might have deliberately seeded life across the cosmos. It's a staggering thought that our existence could be part of someone else's experiment, or even their act of cosmic generosity. Yet for all its poetry, panspermia faces tough questions. Space's brutal radiation, extreme temperatures, and the violence of planetary impacts all pose challenges for fragile organic molecules. Could they really survive an interstellar journey? Experiments on the International Space Station suggest some might. Certain bacteria and even tardigrades, those microscopic extremophiles, have endured the vacuum and radiation of space, hinting that life's raw materials might be hardier than we thought. And then there's the bigger picture. If panspermia is true, life could be astonishingly widespread, a cosmic fugitive, hopping from planet to planet whenever catastrophe strikes. Mars, with its ancient rivers and lakes, might have once shared its molecular bounty with Earth via meteorites blasted into space by asteroid impacts. Even distant exoplanets could be part of this grand exchange, trading the seeds of complexity across light years. So while panspermia doesn't answer how complexity first arose, it reshapes the question into something even grander. Instead of a single origin story, we might be looking at a saga of cosmic cross-pollination, where life's ingredients are universal currency, endlessly traded in the stellar marketplace. It's a humbling reminder that Earth isn't an isolated oasis, it's a participant in a vast, interconnected dance of chemistry that spans the entire universe. This theory forces us to confront an exhilarating possibility, that the search for life's origins doesn't end with our planet. It extends out into the void, to asteroid belts and comet tails, to the swirling dust of nebulae and the frozen oceans of alien moons. The answer might not be buried in Earth's past, but written in the stars themselves, waiting for us to look up and read it. Deep in the frigid void between stars, where temperatures hover just above absolute zero and atoms move sluggishly through darkness, an unlikely architect might have paved the way for complexity cosmic dust. These microscopic grains, no larger than a fraction of a human hair, are scattered everywhere, remnants of ancient supernova or the debris of long-dead stars. On their icy surfaces, chemistry takes on a strange new rhythm. The stillness of space actually helps fragile molecules form, as atoms stick to the dust like climbers finding footholds on a mountain, gradually building structures too delicate to survive anywhere else. Laboratory experiments reveal the astonishing potential of this process. Scientists recreate interstellar conditions by chilling vacuum chambers to near zero temperatures, coating surfaces with ice mimicking cosmic dust, then bombarding them with ultraviolet light or cosmic rays, the same energy sources that permeate space. Within hours, simple molecules like carbon monoxide and water begin linking up, forming sugars, alcohols, and even amino acids. The dust grains aren't just passive platforms. Their irregular shapes create nooks where molecules concentrate, and their mineral cores can act as catalysts, speeding up reactions that would take millennia in open space. One breakthrough came when researchers detected glycolaldehyde, a sugar molecule essential for RNA formation, in a simulated interstellar cloud. This wasn't just a lab curiosity. Astronomers soon found the same molecule floating near a star-forming region 26,000 light-years away. The implications are staggering. The sugar needed for life's genetic machinery might have been baked into the universe's recipe from the very beginning, dust grains serving as tiny ovens where the first sweet whispers of biology emerged. But how does this delicate chemistry survive the journey from deep space to planets? The dust grains might hold the answer. As they clump together in nebulae, they form protective cocoons around their molecular cargo. When these aggregates grow large enough, they become comets or asteroids, celestial arcs that could ferry prebiotic material across solar systems. Heat from impacts or stellar radiation might seem destructive, but simulations show it can actually trigger new rounds of chemical innovation, transforming simple sugars and acids into even more complex structures. Critics argue that space's harsh conditions, intense radiation, violent shocks from supernova should shred fragile molecules, yet nature finds a way. Some dust grains contain pockets of graphite or silicates that shield their icy mantles, while others drift into denser regions of gas clouds where they're buffered from the worst cosmic storms. It's a delicate dance between creation and destruction, with dust grains as both stage and choreographer. This theory reshapes our search for life's origins. If interstellar dust was the universe's first chemistry lab, then the ingredients for life aren't just scattered randomly. They're woven into the fabric of galaxies, waiting for the right planetary conditions to awaken them. Every time we find a new organic molecule in space, from ethanol to formaldehyde, it's another clue that the universe has been quietly, persistently assembling life's toolkit for billions of years. The dust beneath our feet might carry echoes of that epic story, one written not in words but in the silent, steadfast work of countless microscopic scaffolds stretching across the cosmos. Ultraviolet light, often seen as a destructive force, shredding DNA and bleaching surfaces, might have been one of the universe's most unexpected sculptors of complexity. Out in the void, where young stars blast their surroundings with intense UV radiation, a paradoxical process unfolds. Instead of just breaking molecules apart, these high-energy photons can nudge simple compounds into linking up, forging chains that become the backbone of life's chemistry. Picture a cosmic construction zone where light isn't the wrecking ball, but the welder fusing humble molecules into something far grander. Take formaldehyde, one of the most common molecules found drifting through nebulae. On its own, it's just a tiny arrangement of one carbon, two hydrogens, and an oxygen atom, hardly the stuff of wonder. But bathe it in ultraviolet light and something remarkable happens. The energy from the photons knocks electrons loose, allowing formaldehyde molecules to snap together like puzzle pieces, forming long chains called polymers. These aren't just random tangles. Some of these polymers, like polyoxymethylene, have structures eerily similar to sugars, the very molecules that form the backbone of RNA. It's as if the universe has a hidden recipe for complexity, written in light and gas. Astronomers have spotted these formaldehyde polymers in places like the Orion Nebula, where newborn stars drench their surroundings in UV radiation. The discovery raises a tantalizing question. Could these cosmic chains have been delivered to young planets like Earth, seeding them with ready-made ingredients for life? Lab experiments back this up. When scientists simulate nebula conditions irradiating icy mixtures of formaldehyde and water with UV light, they watch as the molecules stitch themselves into longer and longer chains, some even folding into ring-like structures reminiscent of ribose, a key sugar in RNA. But UV's role doesn't stop at simple linking. The same radiation that builds these polymers can also select which ones endure. Shorter chains might get broken apart by subsequent photons, while sturdier, more stable structures survive. It's a brutal but efficient editing process, a galactic version of survival of the fittest where only the most resilient molecules make the cut. Over eons, this could have led to a natural concentration of the very polymers most useful for life's next steps. Critics point out that UV radiation is a double-edged sword. It can create, but it can also destroy. Too much exposure, and even robust polymers might fray back into simpler fragments. Yet nature has workarounds. Dust grains, those microscopic waste stations we discussed earlier, could have sheltered nascent chains in their crevices, letting them grow shielded from the harshest radiation. Or perhaps the polymers formed in dense regions of nebulae, where swirling gas acted like a cosmic sunscreen, filtering the UV just enough to let chemistry thrive without being obliterated. What's truly mind-bending is the scale of this process. Imagine entire nebulas, vast, light-years-wide nurseries of gas and dust, bathed in starlight, quietly assembling molecular chains like an inconceivably large factory. Every second, trillions of these reactions could be happening across the galaxy, a slow, invisible march toward complexity. By the time Earth formed, the building blocks raining down on it might have already been pre-sorted, pre-tested by eons of cosmic trial and error. This theory doesn't just add another page to life's origin story, it rewrites the setting. Instead of a calm, sheltered pond or a deep sea vent, the first steps toward complexity might have taken place in the searing glare of newborn stars, with ultraviolet light as both architect and editor. It's a reminder that the universe doesn't need gentle conditions to create. Sometimes it's the very harshness of the environment that forces molecules to evolve, adapt, and ultimately transcend their simplicity. Quantum tunneling defies everything we thought we knew about chemistry and space. Normally, molecules need energy, heat, light, or pressure to collide and react. But in the near absolute zero emptiness between stars, where atoms move slower than glaciers, traditional reactions should grind to a halt. Yet somehow, complex molecules exist there. The answer might lie in one of the universe's most bizarre tricks: particles teleporting through barriers they shouldn't be able to cross. Think of it like this. Imagine rolling a ball up a hill. Classically, if the ball doesn't have enough energy, it'll roll back down. But in the quantum world, there's a chance, however small, that the ball could suddenly appear on the other side of the hill without ever climbing it. That's quantum tunneling. In the frozen depths of space, hydrogen atoms and other simple particles exploit this loophole, bypassing the need for heat or speed to forge bonds. It's chemistry without the usual rules, a silent, invisible dance where the universe cheats its own limitations. Lab experiments have caught this phenomenon in action. Scientists chilled atoms to just a few degrees above absolute zero, creating conditions mimicking interstellar clouds. Even in this frozen state, reactions occurred slowly but undeniably. Methanol, a precursor to more complex organics, formed at temperatures where classical chemistry says it should be impossible. The implications are staggering. If tunneling lets molecules assemble in the coldest corners of the cosmos, then the building blocks of life might be far more widespread than we ever imagined. But here's where it gets wilder. Tunneling doesn't just enable reactions, it might select which ones happen. Some molecular partnerships, like hydrogen meeting oxygen to form water, tunnel more efficiently than others. This cosmic filtration could explain why certain molecules dominate in space while others are rare. It's as if the universe has a hidden preference for the very compounds life eventually needed. Critics argue quantum effects are too delicate to matter on macroscopic scales, yet discoveries keep proving otherwise. Astronomers have spotted organic molecules in places too cold for traditional chemistry, like the dark cores of nebulae where stars haven't yet ignited. Each detection hints that tunneling isn't just a lab curiosity, it's a silent architect, weaving complexity into the fabric of space itself. This theory forces us to rethink the boundaries of chemistry. The icy voids between stars aren't dead zones, they're quantum playgrounds where particles bend the rules, proving that even in the deepest cold, the universe finds a way to build. Beneath Earth's early oceans and rivers, hidden in the mud and sediment, an unassuming architect might have orchestrated life's first molecular symphonies: clay. These layered minerals, formed from weathered rock and volcanic ash, aren't just lifeless dirt. Their surfaces are riddled with microscopic nooks, charged edges, and honeycomb structures that act like molecular assembly lines, sorting and stitching simple compounds into something far more intricate. Picture a bustling construction site where clay sheets are the foreman, directing workers' molecules into precise arrangements, turning chaos into order one layer at a time. The magic lies in clay's unique structure. Each flake is made of stacked silicate layers with atoms arranged in repeating hexagonal patterns. These layers carry subtle electrical charges, creating a sort of molecular velcro that grabs onto passing organic compounds. Amino acids, sugars, and other building blocks cling to the clay's surface, held close enough to react but organized just enough to avoid random chaos. It's a Goldilocks scenario, not too loose, not too tight, but perfect for fostering complexity. Laboratory experiments reveal how powerful this process could have been. When scientists mix simple organic molecules with montmorillonite, a common clay, something astonishing happens. The clay doesn't just passively host reactions, it supercharges them. In one landmark study, researchers observed clay particles catalyzing the formation of RNA-like strands up to 50 units long, a leap from chemistry toward biology. Even more striking, the clay's layered structure seemed to favor certain molecular arrangements, subtly guiding the process toward patterns we now see in living systems. But clays don't just build, they also select. Their charged surfaces attract some molecules more than others, effectively filtering the chemical soup of early Earth. Fatty acids, for instance, align neatly along clay edges, eventually forming primitive membranes resembling cell walls. Meanwhile, clays rich in metals like iron or nickel could have acted as ancient batteries, fueling reactions with redox energy long before cells evolved their own metabolic tricks. It's as if these unassuming minerals were nature's first laboratories, equipped with built-in tools for sorting, stabilizing, and energizing life's ingredients. Critics question whether clay's orderliness could compete with the riotous energy of hydrothermal vents or the randomness of primordial soups, yet clays offer something neither can match: memory. As layers form and reform, they trap molecules between them, creating a snapshot of successful combinations. Over time, these templates could have honed in on the most efficient pathways, like a cookbook refined through generations. Some researchers even speculate that clay's repeating patterns might have inspired the helical structures of DNA, a literal case of geology guiding genetics. The theory gains traction when you consider how widespread clays are not just on Earth but beyond. Mars' ancient riverbeds are strewn with clay deposits, and asteroids like Ceres show evidence of clay-like minerals. If these unassuming rocks really did midwife life's first molecules, then the recipe for complexity might be written into the very dirt beneath our feet and scattered across the cosmos. It's a humbling thought that the same minerals we walk over every day could hold echoes of the universe's oldest craftsmanship, patiently assembling the pieces of life one grain at a time. Volcanoes have long been symbols of raw destruction, but what if their fury also held the key to creation? Picture an early Earth, its surface scarred by erupting giants spewing ash miles into the sky. Amidst this chaos, an electrifying phenomenon emerges: volcanic lightning. These jagged bolts, generated when ash particles collide and build static charge, aren't just spectacular light shows. They're nature's high-voltage chemistry sets, capable of stitching simple gases into complex molecules in the blink of an eye. Modern eruptions offer clues to this ancient alchemy. When Mount St. Helens erupted in 1980, scientists detected something unexpected in its plume: a cocktail of organic compounds, including formaldehyde and hydrogen cyanide, two molecules crucial for life's building blocks. Similar findings emerged from Iceland's Eyjafjallajökull in 2010, where lightning-filled ash clouds contained traces of amino acids. It's as if volcanoes, while tearing the Earth apart, simultaneously stitched together the very ingredients needed to rebuild. The process hinges on volcanic plumes acting as temporary atmospheres. As gases like water vapor, carbon dioxide, and nitrogen explode upward, they create a swirling reactor where pressure, temperature, and electrical energy collide. Lightning strikes provide sudden bursts of energy, breaking molecular bonds and allowing atoms to recombine in new configurations. But the real magic happens in the ash itself. Microscopic mineral particles rich in iron, sulfur, and silica act as catalysts, lowering the energy needed for reactions and guiding molecules toward complexity. Laboratory experiments back this up. When researchers simulate volcanic conditions by zapping gas mixtures with artificial lightning, amino acids form within minutes. Even more compelling, volcanic ash samples from active vents have been found to host microbial life, hinting that these chaotic environments might not just create molecules but also cradle their evolution toward biology. Yet skeptics raise valid questions. Could delicate organic compounds survive the scalding heat and corrosive chemistry of eruptions? Surprisingly, volcanic plumes have layered zones, scorching at the core but cooler at the edges where molecules might stabilize. And ash fallout moves quickly. Compounds synthesized high in the plume could rain down into nearby oceans or lakes before breaking apart, delivering their precious cargo to more hospitable environments. This theory reshapes our view of Earth's violent youth. Instead of a hindrance to life's origins, volcanoes may have been its relentless midwives, their eruptions not just shaping the planet's surface but also jump-starting its chemistry. The same forces that built continents and scorched skies might have quietly assembled life's first puzzle pieces, one electrified explosion at a time. Looking beyond Earth, the implications are staggering. Mars' Olympus Mons, the solar system's tallest volcano, likely once hosted similar eruptions, meaning the recipe for prebiotic chemistry could have played out there too. Even icy moons like Io, with its ceaseless volcanic activity, might be forging complex molecules in fire and lightning right now. The universe, it seems, has a flair for turning devastation into genesis, proving that sometimes creation requires a little chaos. Cosmic rays, those high-energy bullets screaming across the universe at nearly light speed, might seem like agents of pure destruction, but in the grand chemistry of the cosmos, they could have been the ultimate spark plugs, firing up reactions that transformed simple molecules into the precursors of life. These particles, born in supernova or ejected by quasars, carry enough energy to strip electrons from atoms or even shatter atomic nuclei on impact. Yet in the chaos they leave behind, new molecular bonds can form, stitching together complexity from the wreckage of simpler things. Laboratories have caught this paradox in action. When scientists expose mixtures of water, ammonia, and methane, gases common in interstellar clouds, to beams of high-energy protons mimicking cosmic rays, something remarkable happens. Within hours, the mixture darkens as new compounds emerge, including amino acids like glycine and alanine. It's not gentle chemistry, it's molecular reinvention through violence. The radiation tears molecules apart, but the fragments, now highly reactive, scramble to rebond, often creating configurations too intricate to form under common conditions. One striking example comes from experiments with formamide, a simple organic compound abundant in space. When blasted with radiation, it doesn't just break down, it recombines into adenine, one of the 4 key nucleobases in DNA. This suggests cosmic rays could have been universal suppliers of life's raw materials, raining down not just on early Earth but on planets and moons throughout the galaxy. The implications are staggering. The same radiation that might threaten life today could have been its midwife billions of years ago, but cosmic rays don't work alone. Their effects intertwine with other cosmic processes. In icy interstellar grains, for instance, radiation kicks off chain reactions shielded by the ice itself. As a cosmic ray punches through, it leaves a trail of broken bonds, but the surrounding ice matrix traps the fragments long enough for them to find new partners. Over millennia, this slow cooker effect could build reservoirs of complex organics, frozen in place until a passing comet or asteroid delivers them to a budding planet. Critics argue that radiation-driven chemistry is too random to explain life's precise molecular structures. Yet nature has a way of filtering chaos. Some molecules formed this way are more stable than others, surviving subsequent radiation bouts while less robust ones break apart. It's a brutal but effective form of selection, favoring the compounds that will eventually prove useful to biology. The eerie part, this process isn't confined to the past. Right now, cosmic rays are zipping through nebulae, icy moons, and even Earth's upper atmosphere, potentially forging new organic molecules. The universe might still be cooking up life's ingredients in real time, a cosmic kitchen running on particle beams and starlight. Every time a supernova explodes or a black hole flares, it could be seeding the void with another batch of prebiotic material, whispering the same recipe it used to spark complexity here so long ago. In the frigid expanse of molecular clouds, where temperatures plunge hundreds of degrees below freezing, a microscopic stage is set for one of the universe's most delicate chemical ballets. These vast, murky regions of gas and dust, often called stellar nurseries, are far from inert. Their secret lies in the icy mantles clinging to grains of interstellar dust, each no larger than a speck of pollen. To the untrained eye, these frosty coatings might seem insignificant, but under the right conditions they transform into bustling reactors where simple molecules waltz into unexpectedly complex arrangements. Telescopes like the Atacama Large Millimeter Array have peered into these frozen realms, uncovering surprises. Ethanol, the same alcohol found in beverages, floats alongside formaldehyde and even glycolaldehyde, a sugar linked to RNA formation. How do these molecules assemble in an environment so harsh it should freeze chemistry in its tracks? The answer lies in the ice itself. At temperatures nearing 260 degrees below zero, most chemical reactions grind to a halt. But within the ice's rigid lattice, trapped molecules aren't completely immobile. They inch along via quantum tunneling, hopping between pockets in the ice's structure like commuters navigating a subway. This glacial dance allows reactions to proceed at a pace imperceptible to us but monumental on cosmic timescales. Laboratory experiments reveal the ice's hidden talents. When scientists recreate interstellar conditions by freezing mixtures of water, carbon monoxide, and methane in vacuum chambers, then blast them with ultraviolet light mimicking starlight, something extraordinary unfolds. The ice darkens as new compounds emerge, including amino acids and amphiphiles, molecules that can self-assemble into primitive membranes. The ice isn't just a passive container. Its crystalline structure acts as a template, aligning molecules in ways that favor specific reactions. Hydrogen bonds in the ice lattice even help shuttle protons between molecules, enabling transformations too energy-intensive to occur freely in space. Perhaps most astonishing is how these icy grains become time capsules. When a molecular cloud collapses to form stars and planets, some grains survive, carrying their cargo into newborn solar systems. Comets, those icy wanderers, might be delivery vehicles for these probiotic molecules. In 2014, the Rosetta mission detected glycine, the simplest amino acid in the coma of Comet 67P, a smoking gun linking interstellar ice chemistry to the ingredients of life. Yet mysteries linger. Why do certain molecules dominate in these clouds while others are scarce? Some researchers suggest the ice's layered structure plays matchmaker, with different compounds forming at varying depths. Surface layers exposed to radiation might host simple molecules, while deeper strata shield more fragile assemblies. Others propose that cosmic rays piercing the ice trigger localized hotspots of reactivity, like microscopic forges in the frost. What's undeniable is the scale of this process. A single molecular cloud can span light years and contain enough icy grains to outnumber all the stars in our galaxy. Each one a potential crucible for complexity, quietly assembling pieces of life's puzzle in the dark. This isn't just chemistry, it's the universe's slow, patient craftsmanship, writing the first lines of a story that eventually leads to us. And with every new molecule discovered in these frozen vaults, we're deciphering more of that cosmic blueprint. The implications ripple outward. If ice grain chemistry is universal and given the ubiquity of molecular clouds, it likely is then the raw materials for life aren't rare treasures but cosmic constants. From Europa's subsurface ocean to the frosty plains of Pluto, similar processes could be unfolding right now, weaving complexity in the cold and dark. It's a humbling reminder that life's origins might not demand warmth or sunlight, but simply patience and the quiet alchemy of ice enduring between the stars. Among the countless elements dotting the periodic table, sulfur stands out as an unassuming hero in life's origin story. Picture a steaming, bubbling hot spring on early Earth, its waters thick with dissolved sulfur compounds, its edges crusted with bright yellow mineral deposits. These volatile environments, far from being lifeless wastelands, might have been the universe's first chemistry labs, leveraging sulfur's unique talents to forge the complex molecules that eventually led to us. What makes sulfur so special? For starters, it's a shapeshifter. Unlike many elements that stick to predictable bonding patterns, sulfur can form chains, rings, and even cage-like structures, giving it an unmatched versatility in chemical reactions. Modern metabolism still depends on this trait. Sulfur atoms shuttle electrons in key cellular processes, from photosynthesis to energy production, but its ancient role might have been even more profound. In volcanic vents or acidic hot springs, sulfur compounds like hydrogen sulfide could have acted as both fuel and catalyst, powering reactions that turned simple molecules into precursors for proteins and enzymes. Experiments back this up. When scientists simulate sulfur-rich hydrothermal conditions, they observe amino acids linking into peptide small protein fragments far more efficiently than in neutral water. The secret lies in sulfur's reactive edges. Compounds like thioesters, formed when sulfur bonds with carbon groups, are energy-rich molecules that modern cells still use to drive biochemical reactions. Some researchers argue that these sulfur-based compounds were the original batteries of early metabolism, storing and releasing energy long before ATP evolved. But the sulfur world hypothesis goes deeper. In modern organisms, clusters of iron and sulfur atoms form the heart of many enzymes, hinting at an ancient partnership. These iron-sulfur minerals, abundant near volcanic vents, might have served as primitive templates for life's first electron transfer reactions. Picture a hydrothermal vent's porous rock walls, lined with these conductive minerals, acting like a subterranean electrical grid that energized molecules clinging to their surfaces. Over time, these mineral circuits could have become more sophisticated, eventually giving rise to the metabolic pathways we see today. Critics point out that sulfur-rich environments are harsh, corrosive, toxic, and unstable. Yet that volatility might have been the catalyst life needed. In a world without enzymes to speed up reactions, sulfur's reactive nature could have provided the kickstart chemistry required. And sulfur compounds aren't confined to Earth. They've been detected in interstellar clouds and on Jupiter's volcanic moon Io, suggesting this element's role in cosmic chemistry might be universal. The sulfur world hypothesis doesn't just offer an alternative to the primordial soup. It paints a vivid picture of life emerging from fire and brimstone, where the very element we associate with hellish conditions might have been the spark that ignited biology. From the depths of hydrothermal vents to the iron-sulfur clusters humming in our cells today, sulfur's legacy is written into the fabric of life itself, a reminder that sometimes creation begins where we least expect it. Deep beneath Earth's early surface, where sunlight never reached and volcanic heat was still distant, another power source was quietly at work: radioactivity. The rocks themselves, laced with isotopes like uranium-235 and potassium-40, hummed with energy as their atoms slowly disintegrated over millennia. This wasn't just background radiation, it was a simmering engine that could have cooked up life's first molecules in the most unexpected of places, the fractures and pores of solid stone. The process, called radiolysis, begins when radioactive decay fires off high-energy particles, alpha, beta, or gamma rays that barrel through surrounding material like microscopic wrecking balls. But here's the twist: the destruction fuels creation. When these particles slam into water molecules trapped in rocks, they rip them apart, generating hydrogen gas, hydroxyl radicals, and even hydrogen peroxide. Suddenly, a barren fissure becomes a chemical playground, with free radicals sparking reactions that stitch simple compounds into more complex arrangements. Mineshafts and deep groundwater studies offer real-world proof. In South Africa's Mponeng gold mine, nearly 2 miles underground, scientists found bacteria thriving in water untouched by sunlight for millions of years. The kicker: their energy source was radiolytic hydrogen, produced when radioactive decay split water molecules in the surrounding rock. If single-celled life can subsist on this energy today, it's tantalizing to imagine how the same process could have jump-started probiotic chemistry billions of years ago. Laboratory experiments take it further. Researchers simulating subsurface conditions with uranium-bearing rocks watched as radiation not only produced hydrogen, but also converted carbon dioxide and nitrogen into formate and ammonia, key ingredients for amino acids. The rocks weren't just passive containers, their mineral surfaces acted as catalysts, guiding the chaotic energy of radiation toward productive ends. The scale of this hidden chemistry is staggering. Early Earth's crust was far more radioactive than today, with isotopes like aluminum-26 adding extra heat and energy. Picture vast networks of water-filled fractures, each a microscopic reactor where radiation forged molecules that would later seep into hydrothermal vents or surface pools. Some models suggest radiolyses could have produced more hydrogen in Earth's crust than all volcanic activity combined, a silent, pervasive force shaping the planet's chemistry from the inside out. Critics argue that radiation's randomness makes it an unlikely architect of precise biomolecules. Yet nature has a way of filtering chaos. Certain mineral surfaces, like clays or sulfides, could have organized the products of radiolyses, favoring stable compounds while weeding out weak ones. And radiation isn't uniform, it clusters in hotspots, creating concentrated zones where reactions could build momentum over time. This theory stretches beyond Earth. Mars' subsurface, rich in radioactive thorium and potassium, might harbor similar chemistry even now. Europa's icy shell, bombarded by Jupiter's intense radiation belts, could be undergoing radiolyses in its hidden ocean. The universe might be teeming with these invisible power plants, turning sterile rock into factories of complexity, one atomic decay at a time. Radioactivity's role flips the script on life's origins. Instead of requiring sunlight or volcanic heat, the first steps toward complexity might have unfolded in the cold, dark labyrinth of Earth's crust, powered by the slow, relentless pulse of unstable atoms. It's a humbling thought that the very process we associate with danger and decay could have been the silent midwife to life's first whispers. Imagine an early Earth shrouded in an orange-brown haze, its skies thick with methane and nitrogen, absorbing the sun's ultraviolet rays like a cosmic sunscreen. This wasn't just a gloomy atmosphere, it was a sprawling photochemical reactor, where molecules rising from volcanic vents or surface pools were transformed by the very air they floated in. Far from being a barrier to life's origins, this smog might have been a protective cradle, filtering harsh radiation while cooking up the precursors to biology in its soupy layers. Scientists call this the photochemical smog hypothesis, and it draws eerie parallels to Saturn's moon Titan today. Titan's atmosphere, rich in nitrogen and methane, is veiled in an organic haze so dense it hides the surface from view. When sunlight hits this mix, it triggers a cascade of reactions, creating complex molecules like benzene and cyanide that rain down onto the moon's icy surface. The same process could have unfolded on early Earth, with one critical difference where Titan's frigid temperatures freeze its chemistry in place. Earth's warmer oceans and active geology might have allowed these molecules to accumulate and interact, setting the stage for life. Lab experiments reveal the smog's surprising creativity. When researchers simulate early Earth's methane-rich air in UV-lit chambers, the gas doesn't just break down. It recombines into longer hydrocarbons, including ethylene and acetylene. These compounds, in turn, react with nitrogen to form nitriles, a class of molecules essential for amino acids and nucleotides. The haze acts like a sieve, absorbing destructive UV radiation while allowing just enough energy through to drive these reactions. Over time, the particles grow heavier, settling into lakes or oceans like a slow drizzle of prebiotic ingredients. But the smog's true genius might have been its protective role. Young Earth's sun was dimmer but emitted more high-energy UV light, which could have shredded delicate organic molecules. The haze would have acted as a planetary-scale filter, scattering or absorbing this radiation while letting gentler wavelengths reach the surface. It's a paradox. The same murk that might have made early Earth look hostile could have been the shield that made chemistry possible. Titan offers a tantalizing test case. Data from the Cassini mission showed its haze contains tholins, large, complex organic molecules formed when UV light or cosmic rays zap simple gases. These tholins are far more intricate than anyone predicted, with structures that resemble the building blocks of proteins. If Titan's atmosphere can churn out such complexity in freezing isolation, imagine what Earth's warmer, more dynamic haze could have achieved. Critics argue that smog-heavy skies would have cooled the planet, potentially stalling chemical activity. Yet models suggest the haze might have had a dual role, blocking UV while trapping heat via the greenhouse effect, creating a Goldilocks zone for reactions. And not all haze is equal. Its thickness and altitude could have varied, allowing pockets of chemistry to thrive beneath thinner layers. This theory reshapes our view of early Earth skies. Instead of a clear window to the stars, they might have been a stained glass ceiling, tinted orange by countless chemical reactions. Every sunrise could have painted the smog with new energy, driving another round of molecular innovation. And when the haze finally cleared, perhaps as life began pumping oxygen into the air, it left behind a legacy written into every cell, the proof that sometimes the most uninviting conditions breed the greatest complexity. The lesson extends beyond our planet. If hazy atmospheres are molecular factories, then exoplanets with similar shrouds might be hiding their own chemical symphonies. Telescopes like James Webb are already hunting for haze signatures in distant atmospheres, each detection a potential clue to how common or rare our own origin story truly is. Hidden in the heart of modern proteins, tiny metal clusters pulse with an ancient rhythm: iron and sulfur atoms locked in geometric embrace, shuttling electrons with effortless precision. These unassuming structures, found in enzymes from bacteria to humans, might be molecular fossils, relics of a time before cells, when raw minerals first bridged the gap between geology and biology. Picture a volcanic seep on early Earth, its bubbling waters rich with dissolved iron and sulfide. As these elements mingled, they formed microscopic minerals like pyrite fool's gold, with crystalline lattices that could absorb, store, and transfer energy. The same spark that makes these clusters indispensable today might have made them the universe's first metabolic engines. Modern biology brims with their fingerprints. Nitrogenase, the enzyme that fixes atmospheric nitrogen into life's building blocks, cradles an iron-sulfur cluster at its core. The same goes for hydrogenase, which splits hydrogen molecules, and ferredoxin, a universal electron taxi found in nearly all organisms. This ubiquity hints at something profound. If evolution keeps returning to these structures across wildly different life forms, they likely represent an ancient, optimized solution, one forged in Earth's earliest chemical crucibles. Laboratory experiments reveal why these clusters are so extraordinary. When scientists simulate hydrothermal vent conditions by mixing iron and sulfide ions in oxygen-free water, the particles self-assemble into clusters startlingly similar to those in living cells. Unlike delicate organic molecules, these mineral-based structures are rugged. They tolerate heat, acidity, and radiation that would obliterate other compounds. This durability suggests they could have thrived in the chaotic environments where life first stirred, acting as stable workbenches for increasingly complex chemistry. But iron-sulfur clusters don't just endure, they catalyze. Their unique arrangement of metal atoms allows them to easily gain or lose electrons, making them perfect mediators for redox reactions, the same energy exchanges that power modern metabolism. In vents or volcanic pools, clusters clinging to mineral surfaces might have channeled geothermal energy into chemical work, driving reactions that turned carbon dioxide and nitrogen into formaldehyde and ammonia. Over time, these mineral-bound catalysts could have recruited organic molecules, eventually evolving into the protein-embedded clusters we see today. It's a story written in atomic geometry, the spiral of a fern's frond echoing the angles of pyrite's cubic crystals. The most striking evidence comes from deep-sea vents like those in the Atlantic's Lost City, where alkaline fluids percolate through towering carbonate chimneys. Here, iron sulfide precipitates form honeycomb structures riddled with microscopic pores, each one a potential reactor where molecules could concentrate and react. Some researchers argue these mineral scaffolds didn't just host reactions, they guided them, their conductive surfaces aligning molecules in ways that mimicked early metabolic pathways. The Krebs cycle, a cornerstone of modern metabolism, might have begun as a series of mineral-catalyzed steps on these labyrinthine surfaces, yet skeptics point to gaps. While iron-sulfur clusters excel at electron transfers, they struggle with more intricate tasks like polymerization, the assembly of long molecular chains essential for RNA or proteins. This has led some scientists to propose hybrid scenarios where clusters teamed up with other catalysts like clays or zinc ions to cover each other's weaknesses. Others suggest clusters were just one innovation among many, their success stemming from compatibility with Earth's iron-rich crust rather than primacy in life's origins. The theory's true power lies in its universality. Mars' rust-colored plains testify to its iron abundance, while Jupiter's moon Io spews sulfur-rich plumes into space. If iron-sulfur chemistry truly underpins metabolism, then the recipe for life might be written into the elemental palette of rocky planets everywhere. Every time an enzyme in your body taps into one of these ancient clusters, it's harnessing a trick older than DNA, older than cells, a relic of the moment when Earth's minerals first learned to dance. This isn't just speculation, it's a bridge between the animate and inanimate, proof that the line between rock and life was never as sharp as we imagined. The same forces that tint desert sands red and stain hot springs orange might have been the silent architects of complexity, their molecular handiwork echoing through every living cell on Earth and perhaps beyond. On desert worlds across the cosmos, where howling winds lift towering plumes of dust into thin atmospheres, an invisible force crackles through the chaos static electricity. Picture a Martian dust devil swirling hundreds of feet high, its particles colliding violently enough to strip electrons from atoms. These aren't just storms, they're planet-sized chemical reactors where fleeting sparks could have jump-started the journey from simple molecules to life's blueprints. Spacecraft orbiting Mars have detected eerie glows in these dust storms, evidence of electric discharges powerful enough to alter chemistry. When NASA Perseverance rover analyzed Martian soil, it found perchlorates, salts known to enhance static charging. Combine this with minerals like hematite, and you've got a natural battery generating voltages comparable to laboratory spark reactors. The implications are staggering. While lightning in thunderstorms gets all the attention, these smaller, more frequent discharges in dust clouds might have been the universe's stealthy chemists, working overtime to assemble complexity particle by particle. Lab experiments reveal how transformative this process could be. Scientists recreated Martian conditions by tumbling silicate grains in low-pressure chambers laced with carbon dioxide and nitrogen. As the particles rubbed together, they sparked, and within hours, traces of formaldehyde and hydrogen cyanide appeared. Unlike lightning's brute force approach, dust discharges offer precision, their smaller energy packets favoring specific reactions without obliterating delicate products. It's a Goldilocks scenario, enough energy to break bonds, but not so much that it fries the resulting molecules. The real magic lies in scale. A single dust devil might generate thousands of microscopic discharges per minute, each a tiny crucible for organic synthesis. Now imagine an early Mars or Earth where storms raged for months across entire continents. The cumulative effect could have produced oceans worth of prebiotic material, raining down onto the surface or lingering in the atmosphere. Even today, Titan's hydrocarbon dunes might host similar processes, with grains of water ice and organic compounds charging up as they skitter across frozen plains. Critics argue that dust storms are too chaotic to sustain orderly chemistry, yet nature often turns chaos into pattern. The same turbulence that mixes particles also ensures fresh ingredients constantly enter the reaction zone, preventing stagnation. And dust doesn't just float, it settles, concentrating molecules in dunes or basins where they can interact further. Some models suggest these electric dunes could have acted as planetary-scale sorting machines, with charged particles clustering by composition, effectively grouping reactive molecules together like ingredients laid out for a cosmic chef. This theory expands the stage for life's origins beyond oceans and vents. Arid worlds once written off as barren might have been quietly assembling life's toolkit in their swirling sands. It's a humbling thought that the same forces that choke machinery and stain skies orange could have been the spark that lit the fuse of complexity. From the red plains of Mars to the methane hazes of distant exoplanets, electric dust might be whispering the same recipe it used here billions of years ago, proving that sometimes creation wears the mask of destruction. Water doesn't always play by the rules, especially when it's pushed beyond its comfort zone. Deep below Earth's surface or near searing hydrothermal vents, water enters a twilight state known as supercritical, where it's neither fully liquid nor gas but something far stranger. At temperatures above 700 degrees Fahrenheit and pressures hundreds of times greater than sea level, water's polite molecular structure unravels. Hydrogen bonds fracture, turning it into a ravenous solvent capable of things ordinary water could never achieve. Picture a substance that dissolves oils like acetone but carries minerals like a liquid, all while conducting electricity like a saltwater brine. This isn't just hot water, it's an alchemical fluid, and it might have been the universe's backstage pass to molecular complexity. Supercritical water's magic lies in its split personality. Under normal conditions, water is famously picky about what it dissolves. Oil and water don't mix, right? But crank up the heat and pressure, and those rules flip. Suddenly, water starts embracing organic compounds it usually shuns, breaking them apart or stitching them together in ways that defy textbook chemistry. Laboratory experiments reveal its prowess. When scientists pump carbon dioxide and nitrogen through supercritical water, reactors mimicking ancient hydrothermal systems, amino acids like alanine and glycine emerge within minutes. The same process can even crack long hydrocarbon chains into smaller, reactive fragments, essentially giving nature a toolkit for molecular Legos. Geological evidence suggests these conditions weren't rare on early Earth. Submarine hydrothermal vents like those in the Lost City field gush supercritical fluids today, their chimneys teeming with exotic minerals and organic byproducts. The key is the interface where supercritical water meets cooler surroundings, creating a gradient that sorts molecules by stability. Heat-loving compounds cluster near the vent's core, while more delicate products drift outward, shielded from destruction. It's a natural assembly line, with each thermal zone specializing in a different stage of synthesis. But the real game changer is speed. Supercritical water accelerates reactions that would take millennia at surface conditions. Take peptide bonds, the links between amino acids that form proteins. Normally, forming these bonds requires energy and careful dehydration. In supercritical water, the environment itself becomes the catalyst. The fluid's chaotic structure exposes molecules to extreme forces, bending them into configurations that snap together almost effortlessly. Some researchers compare it to a molecular pressure cooker, where the sheer violence of the environment forges bonds faster than they can break. There's a cosmic twist to this story. Saturn's moon Enceladus, with its subsurface ocean and cryovolcanoes, likely hosts supercritical water interfaces where its icy crust meets a rocky core. NASA Cassini probe detected organic molecules in Enceladus plumes, hinting that this alien chemistry might be universal. Even more intriguing, supercritical water could explain why certain molecules dominate in meteorites. When asteroids experience brief, intense heating during planetary collisions, pockets of water inside them might flash into this state, scrambling simple compounds into complex ones before freezing them in place for delivery to planets. Yet for all its promise, supercritical water has skeptics. Some argue its harsh conditions would shred delicate biomolecules as quickly as it creates them. But nature's solutions are often messy. Mineral surfaces in vents could act as buffers, absorbing the fluid's harshest effects while still harnessing its power. And not all reactions need to be gentle. Sometimes chaos is the crucible that breeds resilience. What emerges is a vision of water not as a passive backdrop for life's origins, but as a dynamic, shape-shifting participant. In its supercritical state, it becomes the universe's ultimate multi-tool destroyer and creator, solvent and scaffold all at once. The same substance that fills our glasses and carves canyons might, under extreme pressure, hold the secret to how simple atoms first crossed the threshold into complexity. It's a reminder that even the most familiar substances can harbor alien potential if we're willing to push them to their limits. When an asteroid the size of a mountain slams into a planet at 30,000 miles per hour, the immediate aftermath is pure devastation: molten rock, towering tsunamis, skies darkened for years. But in that apocalyptic chaos, hidden within the searing heat and unimaginable pressures of the impact zone, nature may have forged one of its most unexpected laboratories. The same forces that wiped out the dinosaurs could have been the universe's hammer, striking an anvil where simple molecules were crushed into complexity. Evidence lies in the minerals left behind, quartz grains fractured in ways only possible under pressures exceeding 500,000 times Earth's atmosphere, or microscopic diamonds forged from carbon in an instant. These shocked minerals aren't just scars of violence, they're chemical catalysts. Under extreme conditions, their crystal structures twist into unusual configurations, creating surfaces that can rip apart molecules or weld them together with unnatural precision. At the Sudbury crater in Canada, a 200-kilometer-wide scar from an ancient impact, geologists found nickel and iron sulfides with jagged atomic edges perfect for stitching carbon monoxide into methane or cyanide, compounds essential for life's building blocks. Laboratory experiments reveal the staggering potential. When scientists simulate asteroid strikes by firing projectiles at mineral samples in high-pressure chambers, the resulting shockwaves transform bland rocks into chemical powerhouses. A mundane piece of olivine, after enduring a simulated impact, suddenly gains the ability to convert nitrogen and hydrogen into ammonia, a molecule crucial for amino acids. Even more striking, these reactions happen in microseconds. Blink and you'll miss it windows where physics behaves radically differently. It's as if the universe compressed millions of years of trial and error chemistry into a single violent flash. The real magic happens in the aftermath. As impact craters cool, they become natural reactors. Hydrothermal systems spring up where groundwater seeps into fractured, still hot rocks, creating zones that mimic the conditions of deep-sea vents, but with an added bonus: impact-synthesized minerals littering the crater floor like microscopic tools. The Houghton crater in the Arctic, formed 23 million years ago, still hosts bizarre microbial communities thriving on these mineral byproducts, proving that impacts don't just destroy, they reset the stage for new chemistry. Critics argue that the sheer energy of impacts would obliterate delicate organics. Yet nature is full of paradoxes. The same shockwaves that vaporize rock can also create protective microenvironments, tiny pockets where pressure and temperature gradients shield molecules long enough to stabilize. And not all impacts are equal. A mid-sized asteroid striking shallow seas could generate just the right mix of heat, minerals, and liquid water to act as a planetary-scale pressure cooker, its effects more surgical than apocalyptic. This theory stretches beyond Earth. Mars's rusty surface is pocked with craters, many of which show signs of ancient hydrothermal activity. The planet's best chance at brewing life's ingredients might not have been quiet ponds, but the brief, furious moments when space rocks turned its crust into a temporary forge. Even icy moons like Europa, with impacts fracturing its frozen shell, could have leveraged these transient zones to jumpstart complexity beneath its alien ocean. Asteroid impacts redefine our view of cosmic chemistry. Where we once saw only cataclysm, we now glimpse a creative force, a universe that sometimes builds not with gentle strokes, but with the brute precision of a hammer shaping molten steel. Every crater, from Earth's battered surface to the moon's dusty plains, might be more than a scar. It could be a signature, a mark left by the universe's most violent yet most ingenious alchemist. Freezing isn't just about preservation, it's a cosmic sorting algorithm, a way for the universe to concentrate rare ingredients into pockets of potential. Imagine a shallow pool on early Earth, its surface shimmering under a pale sun. As night falls, ice crystals begin forming at the edges, their growth pushing dissolved molecules ahead like a microscopic broom. Compounds that were once scattered become densely packed, forced into close quarters where collisions and reactions become inevitable. This phenomenon, called the cold trap effect, might have been nature's first molecular matchmaker, turning frozen water into a factory for complexity. Antarctica's ice cores reveal this process in action today. Locked in their ancient layers are traces of formaldehyde, hydrogen peroxide, and even amino acids, not because they formed there, but because freezing concentrated them. When scientists melt sections of these cores, they find chemical hotspots where impurities accumulated at grain boundaries or within tiny brine channels. These pockets, some no wider than a human hair, become microscopic theaters where reactants that would otherwise ignore each other suddenly find themselves nose to nose, with nowhere to escape but into new combinations. Lab experiments show just how powerful this compression can be. When researchers freeze dilute solutions of simple organics like cyanide or formaldehyde, the resulting ice doesn't just exclude them, it herds them into liquid veins between crystals, boosting their local concentration by 1,000-fold. In these cramped quarters, reactions that would take years in open water unfold in days. One study demonstrated that freezing mixtures of ammonia and glycolaldehyde, a simple sugar precursor, spontaneously generates ribose, the sugar backbone of RNA. The ice isn't just a passive container. Its crystalline structure acts as a catalyst, aligning molecules in orientations that favor specific bonds. The cold trap's genius lies in its cyclical nature. Freeze-thaw cycles, like those on tidal flats or seasonal lakes, would have repeatedly concentrated and mixed molecules, each round winnowing out unstable compounds while amplifying robust ones. Picture a primordial slushy freezing and melting under the rhythms of early Earth's climate, its chemistry growing richer with every cycle. Over millennia, this natural distillation could have built reservoirs of probiotic material, stored safely in ice until warmth released them into waiting environments like volcanic ponds or hydrothermal seeps. But the implications stretch beyond Earth. Mars' polar caps, with their layered deposits of ice and dust, could be hoarding similar chemical treasures. Europa's icy crust, cracked and refrozen by tidal forces, might be executing its own version of this freeze-concentrate chemistry right now. Even interstellar ices, locked in comets or frosty grains, could have used cold traps to assemble complexity before delivering it to young planets. The universe, it seems, has a knack for turning its coldest corners into improbable workshops, places where stillness and repetition conspire to create the very building blocks of dynamism and life. What makes this theory so compelling is its simplicity. No need for lightning strikes or superheated vents, just the patient, universal physics of phase change. Ice exists everywhere temperatures drop, from Martian poles to the shadows of asteroids, making cold traps one of the most democratic crucibles for chemistry in the cosmos. Every snowflake that falls today carries echoes of this ancient process, its delicate structure a reminder that sometimes the path to complexity isn't forged in fire, but in the quiet, persistent grip of the cold. Deep within Earth's molten core, swirling currents of liquid iron generate an invisible force that reaches far beyond the planet's surface, a magnetic field stretching into space like a colossal, dynamic shield. While we often think of magnetism protecting us from solar radiation, its influence might have been far subtler and more profound in life's earliest moments. Picture a quiet tide pool 4 billion years ago, its water laced with simple organic molecules. As Earth's magnetic field pulsed around them, these molecules could have aligned like compass needles, their atomic structures twisting into precise orientations that favored the very handedness we see in life's chemistry today. This isn't just speculation, it's a phenomenon rooted in physics. Certain molecules, especially those with asymmetrical structures, respond to magnetic fields like dancers to music, their electrons shifting in ways that subtly bias their geometry. Modern biomolecules display a peculiar quirk called homochirality. Amino acids almost exclusively lean left-handed, while sugars in DNA spiral right. This uniformity is eerie, since non-living chemistry typically produces equal mixes of both versions. Something must have tipped the scales, and Earth's magnetic field, steady and pervasive, could have been the invisible hand guiding that selection. Laboratory experiments reveal tantalizing clues. When scientists expose chiral molecules to strong magnetic fields while they form, the resulting batches show slight but measurable imbalances, up to 2% more of one-handedness than the other. That might sound negligible, but over millennia, in tide pools or hydrothermal vents constantly bathed in Earth's field, these tiny biases could have amplified. Imagine a feedback loop where aligned molecules catalyzed more of their own kind, gradually crowding out their mirror image counterparts. The mechanism hinges on a quantum oddity called the magnetochiral effect. Asymmetric molecules interacting with a magnetic field can absorb light differently depending on their orientation, creating an energy preference for one chiral form over another. Early Earth's surface, bombarded by polarized sunlight, might have supercharged this process. UV rays selectively breaking down one molecular handedness while magnetism stabilized the other. It's a cosmic filtration system where physics acted as nature's first quality control. Critics argue that Earth's field is too weak to drive such selectivity alone. Yet combined with other forces like the spin-polarized electrons in mineral surfaces or the vortices of tidal flows, magnetism could have been the quiet coordinator, nudging randomness into order. Even more compelling, Mars and Venus, both lacking strong magnetic fields today, show no chiral preferences in the sparse organic molecules detected there. Coincidence? Perhaps not. The implications stretch beyond Earth. Exoplanets with robust magnetic fields might be more likely to develop homochiral biochemistry, a hidden factor in the recipe for life. Meanwhile, lab studies now use magnetic fields to engineer chiral drugs, proving this force's enduring role in molecular craftsmanship. Every time you admire the spiral of a seashell or the twist of a vine, you're witnessing a legacy shaped in part by the silent pull of Earth's ancient magnetism, a force that didn't just shield life's cradle but might have helped sculpt its very blueprint. The edges of ancient shorelines might not seem like prime real estate for molecular innovation until you consider the quiet magic of tidal pools. These shallow basins, filled and drained by the rhythmic push and pull of the moon, create something extraordinary, cycles of wet and dry that transform stagnant puddles into rhythmic chemical reactors. Picture a sun-baked rocky basin at low tide, its concentrated soup of amino acids and salts drying into a glistening crust. Then, as waves return, those same molecules rehydrate, mingling in new configurations. This isn't just evaporation, it's nature's pulse, a metronome that could have driven simple compounds to stitch themselves into life's first polymers. Lab experiments reveal the power of this push and pull. When scientists simulate tidal pool conditions by alternating wet and dry phases in chambers loaded with amino acids, something remarkable happens. As water evaporates, the molecules crowd together, overcoming the usual barriers to bonding. The dry phase acts like a molecular vise, squeezing out water molecules that would otherwise hinder linkages. Then, rehydration washes away unstable byproducts, leaving behind the sturdiest chains peptides, the precursors to proteins. One study at Georgia Tech found that these cycles could produce chains up to 14 amino acids long in just a few days, a blink in geological time. The process is so efficient it's been dubbed nature's forgotten reactor, but the real elegance lies in the cycle's selectivity. Not all molecular pairings survive the tidal pool gauntlet. Fragile bonds break under the stress of repeated drying, while robust ones endure. Over thousands of cycles, this natural editing favors the very structures that would later become central to biology. It's a form of proto-evolution where chemistry is honed not by competition, but by the relentless rhythm of the tides. Modern analogues hint at how transformative this could have been. In Chile's Atacama Desert, one of Earth's driest places, rare rain showers awaken microbial life in salt flats organisms that survive desiccation by producing protective peptides strikingly similar to those formed in tidal pool experiments. Coincidence or evidence of a mechanism so universal that life, once born from it, never forgot the recipe? The implications stretch beyond Earth. Mars' ancient shorelines, now bone dry, might still preserve the chemical echoes of similar cycles in their mineral crust. Even Saturn's moon Titan, with its methane tides, could host an alien version of this process where hydrocarbons take the place of water in an icy, slower motion dance. Tidal pools redefine simplicity. No need for volcanic fury or interstellar delivery, just the patient lapping of waves, the heat of a young sun, and time. In that unassuming ebb and flow, the universe might have found its most reliable rhythm, a backbeat so steady it could coax chaos into order, one droplet at a time. Deep beneath Earth's surface, where the crust fractures into a labyrinth of porous rock, an invisible force was quietly at work. Temperature. Not just heat, but the difference in heat, the slow climb from cool surface layers down to the molten mantle. This geothermal gradient, often overlooked in favor of flashier energy sources like lightning or UV radiation, might have been the universe's most patient chemist, turning ordinary stone into a sprawling reactor where molecules could harness Earth's inner fire. Picture a network of water-filled pores threading through volcanic rock. Near the surface, groundwater seeps in at ambient temperatures, but just a few hundred meters down, the rocks grow warmer. As this water percolates deeper, it heats up, expanding and rising through convection, only to cool again as it loops back toward the surface. This creates a dynamic cycling system, a natural pump driving fluids through cracks and crevices, where each temperature shift alters the water's chemistry. Warm water dissolves minerals like silica and iron more readily, while cooling releases them, creating microscopic deposits that act as catalysts. The result: a self-sustaining engine where energy isn't just present, it's flowing, creating gradients ripe for molecular innovation. Modern analogs reveal the power of this process. In gold mines kilometers below South Africa, scientists discovered entire ecosystems of bacteria thriving in fractures where geothermal gradients persist. These microbes don't rely on sunlight or organic debris. They tap into chemosynthesis using hydrogen and sulfates generated by reactions between water and hot rock. The kicker: these reactions are abiologic, driven purely by geology. If single-celled life can exploit these gradients today, it's plausible that billions of years ago, similar conditions could have fueled probiotic chemistry, stitching simple molecules into ever more complex arrangements. Lab experiments confirm the potential. When researchers simulate geothermal gradients in columns packed with basalt and water, they observe a cascade of reactions: carbon dioxide converting to formate, nitrogen fixing into ammonia, even the occasional appearance of amino acids. The porous rock acts like a chromatograph, sorting molecules by their affinity for temperature zones. Hotter regions favor bond breaking, while cooler areas become assembly sites where fragments recombine. Over time, this sorting could have created concentrated pockets of reactive compounds, turning Earth's crust into a three-dimensional puzzle where only the most stable molecular partnerships endured. What makes geothermal gradients so compelling is their ubiquity. Unlike hydrothermal vents or tidal pools, which require specific geological settings, temperature differentials exist anywhere a planet has internal heat and liquid water. Mars' subsurface, with its ancient volcanic provinces and evidence of groundwater, likely hosted similar gradients. Even icy moons like Europa, warmed by tidal friction, might conceal rocky interfaces where freezing oceans meet a heated core, creating the same kind of energy flow that could have jump-started chemistry here. Yet skeptics argue that without a focusing mechanism, these reactions would be too dispersed to build real complexity. But nature has solutions. Mineral surfaces like pyrite or clays could have trapped and concentrated molecules, while convection cycles ensured fresh ingredients constantly entered the reaction zone. And geothermal systems aren't static, they evolve over millennia, meaning a successful molecular experiment in one epoch could be transported to new environments as the crust shifts and fractures. The takeaway is profound. Life's origins might not have required a single dramatic setting, but rather the slow, pervasive work of Earth itself. its heat, its fractures, its unyielding gradients acting as both incubator and architect. Every volcanic plain, every tectonic rift, every seep of groundwater carries echoes of this ancient process, reminding us that sometimes the most powerful chemistry happens not in fire or ice, but in the quiet, persistent spaces between. Beneath the restless surface of Earth's early oceans, an unseen force was pulsing through the water sound. Not the gentle lapping of waves, but the intense, low-frequency rumble of seismic activity, hydrothermal vents, and even meteorite impact. These vibrations didn't just travel through the water, they shaped it, creating microscopic pockets of chaos where the ordinary rules of chemistry bent. Imagine a sound wave so powerful it tears the water apart for just an instant, forming tiny voids that collapse with such force they generate temperatures hotter than the sun's surface and pressures rivaling the Mariana Trench. These fleeting infernos, known as acoustic cavitation bubbles, might have been nature's most unexpected crucibles, forging complex molecules in their violent dance. The phenomenon isn't just theoretical. Modern labs use ultrasound to intentionally create cavitation bubbles in a field called sonochemistry. When high-frequency sound waves pass through water, they generate alternating zones of high and low pressure. In the low-pressure phase, liquid water fractures, forming vapor-filled cavities. Then, when the pressure swings back, these bubbles implode with astonishing violence, compressing the gas inside to thousands of degrees Kelvin. For a fraction of a microsecond, these hotspots become laboratories where impossible reactions unfold, nitrogen fixing into ammonia, carbon dioxide reducing to formaldehyde, even water molecules splitting into radicals that attack organic compounds, stitching them into new configurations. One landmark experiment at Oak Ridge National Laboratory demonstrated this power starkly. Researchers exposed a simple solution of water, nitrogen, and carbon monoxide to ultrasound. Within hours, the mixture bubbled with glycine, the simplest amino acid, along with traces of alanine and serine. No enzymes, no catalysts, just sound ripping apart molecules and reassembling them into life's building blocks. The process mirrors what might have occurred near ancient hydrothermal vents, where boiling fluids and seismic tremors could have generated a constant underwater symphony of collapsing bubbles. But cavitation's genius lies in its selectivity. Unlike uncontrolled heat, which tends to obliterate delicate organics, bubble collapse is intensely localized. The surrounding water remains cool, acting as a heat sink that quenches reactions before they can reverse. This creates a Goldilocks scenario, enough energy to drive synthesis, but not so much that it fries the product. Even more striking, the bubble's collapse isn't perfectly symmetrical. They implode in microjets that shear nearby molecules, creating reactive edges perfect for polymerization. Some researchers speculate this could explain how early peptides linked up without enzymes, their chains elongating in the hydrodynamic chaos. The theory gains traction when you consider how common acoustic energy would have been on early Earth. Submarine earthquakes, erupting vents, even the crash of tidal waves onto rocky shores, all would have sent shockwaves through the oceans, churning the water with cavitation. And unlike lightning or UV radiation, which are sporadic or surface-bound, sound propagates uniformly through liquid, turning entire ocean basins into potential reactors. Even today, divers near active underwater volcanoes report the eerie sensation of feeling the sound as much as hearing it, their bodies vibrating from infrasound too low for human ears. 4 billion years ago, that primal hum might have been the backdrop to chemistry's first steps toward complexity. Critics point out that cavitation is too chaotic to explain life's molecular precision. Yet nature thrives on harnessing chaos. Mineral particles or lipid films could have stabilized bubble interfaces, creating semi-protected zones where reactions could build momentum. And not all cavitation is equal frequency matters. Low-frequency waves generate fewer but more energetic collapses, while high frequencies produce gentler, more numerous bubbles. A mix of both, as would occur in a dynamic early ocean, could have offered a spectrum of conditions for different stages of molecular evolution. The implications ripple beyond Earth. Europa's subsurface ocean, flexed by Jupiter's gravity, likely experiences tidal quakes that could drive cavitation. Even Saturn's moon Enceladus, with its icy geysers, might host similar processes where water jets collapse back into the subsurface sea. The universe, it seems, has a knack for turning vibrations into creation, proving that sometimes the most silent depths hide the loudest chemistry. Light pulses through a shallow tide pool on early Earth, not as a passive glow but as a scalpel splitting electrons with surgical precision to power chemistry no ordinary reaction could achieve. This is photon-driven electron bifurcation, a phenomenon so counterintuitive it bends the rules of energy transfer. Imagine sunlight striking a cluster of iron-sulfur minerals submerged in water. Instead of merely heating the surface, that light excites electrons in the mineral's atomic structure. But here's the twist: each energized electron doesn't take a single predictable path. It splits, with one fragment rocketing off to drive high-energy reactions while the other stabilizes nearby molecules. It's nature's version of a power grid, where sunlight becomes a dual-current battery for molecular innovation. Modern microbes still exploit this trick today. Certain bacteria use electron bifurcation to survive in extreme environments, channeling the energy from a single electron into two separate tasks, one fraction reducing carbon dioxide, the other pumping protons across a membrane to store energy. The efficiency is staggering, allowing organisms to thrive where traditional photosynthesis would fail. But the roots of this mechanism might stretch back to Earth's infancy, when mineral surfaces served as primitive analogues to today's protein complexes. Lab experiments with synthetic iron-sulfur clusters show that when bathed in simulated sunlight, these minerals can bifurcate electrons without any biological machinery. Place them in a solution mimicking early Earth's oceans, and suddenly you're watching light-driven chemistry produce hydrogen from water or reduce nitrogen to ammonia, reactions essential for life's building blocks. The brilliance of this system lies in its economy. Unlike classic photosynthesis, which requires elaborate chlorophyll structures, electron bifurcation could have operated on bare mineral scaffolds. Picture a hydrothermal vent's porous walls, flecked with pyrite and bathed in the faint glow filtering through shallow water. Each photon's energy gets divided, like a chef finely portioning ingredients, with one electron fragment fueling carbon fixation while the other maintains the mineral's reactivity. Over time, these mineral hubs might have attracted organic molecules, eventually evolving into the protein complexes we see in modern cells, but the implications stretch beyond Earth. Mars' ancient lakebeds, strewn with iron-rich sediments, could have hosted similar light-driven reactions during its wetter eras. Even ice-covered worlds like Europa, where cracks in the ice admit faint sunlight, might leverage electron bifurcation in subsurface mineral layers. The universe, it seems, has a preference for multitasking, turning simple photons into architects of complexity. Critics argue that without precise molecular control, bifurcated electrons would dissipate uselessly. Yet nature thrives on imperfection. Early mineral surfaces likely wasted vast amounts of energy, but in a world with no competition, even inefficient reactions could accumulate products over millennia. And minerals aren't static. Their defects and irregularities create natural hotspots where electrons behave unpredictably, sometimes stumbling into configurations that stabilize their split paths. This isn't just chemistry, it's chaos with direction, like a river carving a canyon, one erratic twist at a time. What emerges is a vision of light, not as a mere energy source, but as a master puppeteer of electrons. The same sunlight that warms your skin today might have orchestrated life's first energy networks, proving that even the simplest physical laws can conspire toward complexity when given enough time and the right atomic collaborators. Buried in the muddy quiet of ancient ocean floors, a silent alchemy unfolded, one where rust wasn't decay but a catalyst. Metal oxides, those unassuming compounds formed when oxygen meets iron or manganese, might have been the universe's first electron accountants, shuffling charges between molecules with the precision of a molecular stock exchange. This isn't just corrosion, it's redox chemistry stripped to its essence, where minerals acted as both scaffold and conductor, bridging the gap between geology and biology. Take manganese nodules, those lumpy, potato-sized concretions that litter abyssal plains. To the untrained eye, they're geological curiosities, but peer closer, and their layered structures reveal a history of electron trafficking. Manganese oxides within these nodules exist in multiple oxidation states, meaning they can effortlessly grab electrons from one molecule and hand them off to another. Modern research shows these minerals excel at mediating reactions critical for life's blueprint, like converting nitrite to nitrate or ferrous iron to ferric. In essence, they're fossilized circuit boards, proof that inorganic chemistry could have run precursor metabolism long before enzymes evolved. Laboratory experiments bring this process to life. When scientists simulate ancient seafloor conditions by mixing manganese oxides with simple organics like formate or ammonia, the minerals don't just sit idle, they actively reorganize electrons, driving reactions that produce glycine or even acetic acid. The manganese isn't consumed, it's a reusable tool, cycling between oxidation states like a molecular swing shift. What's striking is how little energy this requires: no lightning strikes or UV radiation, just the quiet give and take of electrons passing through mineral intermediaries. The real elegance lies in the nodule's structure. Their concentric layers, built over millennia, create a labyrinth of microenvironments. Some zones stay oxygen-rich, ideal for oxidizing reactions, while deeper layers turn anoxic, favoring reduction. This gradient turns each nodule into a self-contained universe of chemical possibility, where molecules could shuttle between zones, undergoing stepwise transformations impossible in open water. Picture a molecular assembly line where manganese oxides act as quality control, ensuring each reaction happens in the right sequence before passing its product deeper into the nodule's heart. Critics argue that redox minerals lack the specificity of enzymes, making them too chaotic to guide meaningful biochemistry, yet chaos can be productive. Modern hydrothermal vent ecosystems thrive on similar mineral-mediated reactions, with bacteria clustering around iron-rich rocks to harness their electron-shuttling power. And manganese's versatility is no accident. Its ability to adopt multiple oxidation states mirrors the very electron carriers like NAD that power cellular metabolism today. It's as if life internalized these mineral tricks, replacing rocks with proteins but keeping the core logic intact. The implications stretch beyond Earth. Mars' Meridiani planum, strewn with hematite concretions similar to manganese nodules, might have hosted analogous chemistry in its ancient seabeds. Even icy moons with subsurface oceans could leverage redox active minerals at rock-water interfaces, turning frozen depths into electrochemical workshops. The universe, it seems, has a penchant for turning rubble into reactors, proving that sometimes the humblest materials hold the keys to complexity. What emerges is a vision of Earth's crust not as a passive stage for life's origins, but as an active participant, its minerals humming with electron traffic, its nodules bustling with molecular trade. The same processes that stain rocks red or blacken volcanic glass might have been the training wheels for biology, steadying chemistry's first wobbly steps toward order. In this light, every rusted canyon and stream bed isn't just weathering, it's a monument to the universe's relentless ingenuity, etching its deepest secrets into the very stones beneath our feet. When a shockwave rips through the atmosphere at supersonic speeds, it doesn't just make noise, it rewrites chemistry. Picture the aftermath of a massive asteroid impact or a superbolt of lightning, where the air itself is compressed into a fleeting but brutal front of pressure and heat. These atmospheric shockwaves act like invisible fists, punching molecules with enough force to snap bonds and forge new ones in configurations that would normally require extreme conditions. What seems like destruction is actually creation in disguise, a cosmic pressure cooker where chaos births complexity. Laboratories have harnessed this phenomenon to simulate the violence of early Earth. In shock tubes, specialized chambers where gases are hit with controlled bursts of energy, scientists observe simple mixtures of methane, ammonia, and water vapor transforming into amino acids and nucleobases within microseconds. The key lies in the shockwave's dual nature. Its leading edge heats gases to thousands of degrees, breaking molecules apart, while the trailing cool zone lets those fragments recombine into sturdier structures. It's a 1-2 punch of destruction and assembly, nature's way of hitting the reset button on chemistry. One study at Stanford even produced glycine, the simplest amino acid, by firing projectiles at gas-filled capsules mimicking asteroid impact. The results were unambiguous. Shockwaves don't just mix ingredients, they reshape them. The real magic happens in the gradients. As a shockwave expands, it creates layers of varying temperature and pressure, each hosting different reactions. The hottest zones might crack nitrogen molecules into reactive atoms, while slightly cooler regions allow those atoms to bond with carbon fragments, forming cyanide, a molecule toxic to us but essential for prebiotic chemistry. Farther out, where temperatures drop further, sugars and amino acids stabilize. This stratification means a single event can generate a spectrum of compounds, sorted neatly by their thermal resilience. Imagine a molecular assembly line where each station specializes in a different step, all orchestrated by the physics of a passing wave. Earth's early atmosphere would have been a symphony of these shocks. Volcanic eruptions, meteorite impacts, and even intense thunderstorms 4 billion years ago. These events were far more frequent and violent than today. Each one sent ripples through the air, turning vast swaths of the sky into temporary reactors. And the products didn't just vanish, they rained down. Models suggest that after a large impact, organic molecules synthesized in the shockwave could condense onto dust particles, drifting into oceans or lakes like a slow-motion fertilizer. Over time, these deliveries might have stocked Earth's waters with prefabricated ingredients for life. But here's the twist: shockwaves might explain some of life's quirks. Recent experiments show that certain amino acids form more readily under shock conditions than others, mirroring the biases seen in biological systems. Could the violent physics of early Earth have subtly steered chemistry toward the compounds life eventually favored? It's a provocative idea that our molecular preferences were imprinted by ancient cataclysms, written into the very fabric of our cells. Yet skepticism lingers. Critics note that most shock-synthesized molecules are simple building blocks, not complex polymers, but nature rarely works in single steps. Shockwaves could have supplied the raw materials, while tidal pools or hydrothermal vents assembled them into larger structures. And shock chemistry isn't confined to Earth. Mars, with its thinner atmosphere and history of impacts, might have experienced even more intense wave-driven reactions. The rover's detection of nitrates in Martian soil, compounds easily formed by shock-induced nitrogen fixation, hints at this process unfolding next door. What emerges is a vision of the young solar system as a firing range, where collisions and eruptions weren't just disasters, they were workshops. Every boom and crash chiseled away at randomness, carving out molecular order from the noise. The echoes of those ancient shocks might still resonate in us today, buried in the structures of our proteins, a reminder that sometimes progress begins with a bang. The afterglow of creation still lingers in the emptiness of space, a faint whisper of heat from the universe's birth known as the cosmic microwave background. This bath of microwave radiation, now cooled to just 2.7 degrees above absolute zero, permeates every cubic centimeter of the cosmos like a ghostly fingerprint of the Big Bang. But 4 billion years ago, when Earth's first molecules were taking shape, this background glow was warmer, brighter, and far more influential. What if this universal energy field didn't just passively fill space, but actively shape the stability and trajectories of the earliest complex molecules? Physics offers a tantalizing clue. Every molecule vibrates at specific frequencies, absorbing and emitting energy like a microscopic antenna tuned to cosmic stations. Today's microwave background is too weak to noticeably affect molecular bonds. Its photons carry barely a trillionth the energy needed to break typical chemical links. But roll the cosmic clock back to when the universe was 1/10 its current age, and the background radiation would have been intense enough to match the vibrational frequencies of many small organic molecules. Picture an infant cosmos where the afterglow of creation hummed at precisely the right pitch to nudge molecules like formaldehyde or hydrogen, cyanide into excited states, altering their reactivity in ways we're only beginning to understand. Laboratory experiments hint at this phenomenon's potential. When scientists expose simple organic compounds to microwave radiation tuned to their resonant frequencies, something remarkable happens. Reaction rates shift dramatically. In one study at the University of Hawaii, microwaves accelerated the formation of glycine from ammonia and formaldehyde by a factor of 20. The radiation didn't provide raw energy like heat would. Instead, it specifically excited molecular vibrations that lowered activation barriers, effectively greasing the wheels of chemistry. Now amplify this effect across an entire young universe, where every molecule existed in a sea of resonant background photons, and suddenly the cosmic microwave background transforms from a silent observer into an active participant in molecular evolution. The timeline is eerily compatible. During the epoch when the background radiation's temperature matched key molecular frequencies roughly between 200 million and 1 billion years after the Big Bang, the first generation of stars was seeding the cosmos with heavier elements. As these elements cooled in interstellar clouds, they'd have encountered a radiation field perfectly poised to influence their assembly. Carbon monoxide molecules might have aligned with the background's 3 Kelvin peak, while water's bending mode resonated strongly at the universe's 10 Kelvin phase. This isn't just theoretical. Astronomers have already detected subtle interactions between modern molecules and the cosmic microwave background in interstellar clouds, where the radiation slightly alters molecular energy states. Critics counter that the background's influence would have been too diffuse to overcome local conditions on planets or in nebulae. Yet mathematics tells a different story. Calculations show that in low-density environments like molecular clouds where complex molecules first assembled, the omnidirectional pressure from the cosmic microwave background could have exceeded the thermal energy of the gas itself. This means the radiation wasn't just a whisper, it was a dominant force, gently but relentlessly pushing molecules toward configurations that maximized energy absorption. Over astronomical timescales, this persistent nudging might have acted as a cosmic filter, favoring the survival of molecular structures that could efficiently interact with the background field while destabilizing those that couldn't. The implications ripple through astrobiology. If the cosmic microwave background helped select early molecular architectures, then life's chemistry might carry hidden signatures of this universal selection pressure. Modern enzymes, for instance, still exploit microwave frequency vibrations in their catalytic mechanisms, a vestige of a time when resonating with the universe's background hum conferred survival advantages. Even more profound is the possibility that different cosmic epochs produced different molecular biases. A civilization emerging when the background radiation was 5 Kelvin instead of 3 might have evolved biochemistry tuned to entirely different vibrational sweet spots. This theory transforms our view of the cosmic microwave background from a passive relic into an active sculptor, a silent conductor orchestrating chemistry on a galactic scale. The same radiation that today quietly permeates your living room as static on an old television might have once played matchmaker to the molecules that made you. It's a humbling reminder that the universe doesn't just provide the stage for life's drama, it whispers cues to the actors, guiding them toward complexity one resonant vibration at a time. High above Earth's ancient surface, where the atmosphere thins into a hazy frontier, an invisible molecular ballet might have unfolded, one where simple hydrocarbons collided, tangled, and stitched themselves into sprawling chains without a single drop of liquid to guide them. This is aerosol polymerization, a process so counterintuitive it challenges our terrestrial biases about where complexity can arise. Picture a sky thick with methane and ethane, molecules buffeted by winds and electrified by solar radiation. Under these chaotic conditions, single carbon links could have snapped together like magnetic beads, forging polymers that rained down as organic confetti onto the young planet's oceans and land. The mechanics defy expectations. Normally, polymerization requires solvents or catalysts to stabilize reactions. But in the free-floating chaos of an aerosol droplet, the rules change. When ultraviolet light fractures a hydrocarbon like methane into reactive radicals, these fragments don't just drift apart. Trapped in microscopic liquid or solid particles suspended in air, they jostle against neighbors with nowhere to escape, increasing the odds of collisions that form longer chains. It's chemistry without a container, where the very instability of the environment becomes its greatest asset. Lab studies simulating early Earth's upper atmosphere show this vividly. When irradiated hydrocarbon mixtures are sprayed into reaction chambers as fine aerosols, they spontaneously generate complex organics like ethylene and even aromatic rings, structures typically associated with industrial synthesis, not primordial skies. Cassini's observations of Titan offer a breathtaking reality check. Saturn's orange-smudged moon is shrouded in hydrocarbon lakes and an atmosphere teeming with organic aerosols, a dynamic that might mirror Earth's probiotic haze. The spacecraft's mass spectrometers detected polymers with molecular weights exceeding 1,000 daltons in Titan's upper atmosphere, far heavier than anyone predicted. These aren't mere methane fragments, they're intricate macromolecules, some with branching architectures resembling the building blocks of kerogen, the organic precursor to fossil fuels on Earth. The parallels are irresistible. If Titan's photochemical smog can spontaneously assemble such complexity under its frigid, nitrogen-rich skies, why couldn't a warmer, water vapor-laden early Earth have done the same? A critical clue lies in the energy gradients. Titan's aerosols form in layers where UV light and cosmic rays interact with atmospheric methane, creating vertical zones of increasing complexity. Higher altitudes host simple molecules like acetylene and hydrogen cyanide, while deeper layers accumulate heavier polymers. Early Earth's atmosphere, though different in composition, likely exhibited similar stratification. Volcanic outgassing would have lofted hydrocarbons high into the stratosphere, where intense sunlight could fracture them into reactive pieces. As these particles drifted downward, they'd encounter fluctuating temperatures and pressures, allowing stepwise assembly into ever more complex structures, a literal skyfall of organic innovation. The implications rewrite conventional origin stories. Unlike tide pools or vents, which localize chemistry to specific environments, aerosol polymerization could have operated planet-wide, turning the entire atmosphere into a three-dimensional reactor. And the products wouldn't just rain down randomly. Wind patterns might have concentrated them in certain regions, creating organic hotspots where delivery rates outpaced degradation. Imagine coastlines dusted with a continual shower of pre-processed molecules, each polymer particle a tiny time capsule preserving reactions that took months or years in the skies above. Yet challenges remain. Without a protective solvent, how did these fragile chains survive descent through oxygen-free but still reactive atmospheres? Here, nature's ingenuity shines. Some models suggest the polymers themselves acted as shields, their outer layers sacrificially absorbing UV damage while protecting inner structures, a molecular analog to spacecraft heat shields. Others point to coating by sulfur or nitrogen compounds, which could have stabilized the organics long enough to reach the surface. The most profound insight might be universality. From Titan's methane rivers to the hydrocarbon-rich atmospheres of exoplanets, aerosol polymerization offers a template for complexity that doesn't rely on liquid water or geothermal energy. It's a reminder that the universe's chemical playbook is vaster than we imagined, one where even the winds, given time and the right ingredients, can weave the threads of life. Bioluminescence, the eerie glow of fireflies, the shimmering waves of ocean algae, is often seen as nature's fireworks, a dazzling but seemingly secondary trait. But what if this light wasn't just a late evolutionary flourish, but one of life's original blueprints? Imagine a primordial Earth where chemical reactions didn't just store energy, they glowed, casting faint luminescence across tidal pools or volcanic seeps. This isn't fantasy. Modern bioluminescence might be a living relic of an ancient molecular language, one where light production predated even the earliest metabolic networks. At its core, bioluminescence is a redox reaction, a dance of electrons where energy escapes not as heat, but as photons. Today, organisms like jellyfish use luciferin and luciferase enzymes to control this glow with precision. But strip away the biological machinery, and you're left with something profound. Simple molecules like aldehydes and peroxides can emit light when they react, no enzymes required. Lab experiments reveal that under probiotic conditions, mixtures of hydrogen peroxide and fatty acids compounds likely abundant near hydrothermal vents produce faint chemiluminescence. It's a glimpse into a world where chemical chaos didn't just simmer in darkness, it pulsed, signaling reactions in progress. The real clue lies in modern organisms that repurpose light for survival. Deep-sea bacteria, for instance, use bioluminescence to attract hosts, but their light-producing genes share striking similarities with those involved in detoxifying oxygen. This hints at an ancient pivot. A system that once dealt with reactive oxygen species might have later co-opted its byproduct light for communication. If early cells harnessed these glowing reactions to manage environmental toxins, bioluminescence could have been a happy accident that evolution refined into a tool. Critics argue that light emission seems too energy-intensive for primitive systems, yet nature thrives on repurposing inefficiencies. A reaction releasing photons instead of heat might have actually protected delicate molecules nearby, preventing thermal damage in crowded microenvironments. And light isn't just waste, it's information. In tide pools or thin films of water, a flicker could have marked spots where redox reactions were most active, guiding other molecules toward productive collisions. Over time, these flashes might have evolved into coordination signals, the precursors to modern cellular communication. The most tantalizing evidence comes from abiogenic light production still occurring today. Certain mineral surfaces, like those of zinc sulfide crystals found in hydrothermal vents, emit photons when stressed by heat or pressure. Early Earth's crust, riddled with such minerals, might have been dotted with natural lighters, their glow catalyzing or stabilizing nearby organic reactions. It's a poetic thought that life's first spark wasn't just metaphorical but literal, a flicker in the dark that eventually built the fire. This theory flips our view of bioluminescence from decoration to cornerstone. The same chemical tricks that make fireflies enchant summer nights might have been the universe's first way of whispering, "Here, this path leads forward." In that light, every shimmering wave or glowing mushroom becomes more than spectacle. It's a living fossil, a beacon from a time when chemistry was still learning how to shine. Quantum mechanics isn't just the domain of lab experiments or futuristic technology. It might have been the universe's hidden choreographer, orchestrating the first delicate steps toward complexity in the coldest, darkest corners of space. Lurking within the vast molecular clouds where stars are born, an eerie phenomenon called quantum coherence could have synchronized the behavior of molecules across staggering distances, turning these cosmic nurseries into precision workshops for prebiotic chemistry. This isn't science fiction, it's a radical reimagining of how randomness might have given way to order, with subatomic particles whispering to one another through the fabric of reality itself. At first glance, the idea seems impossible. Quantum effects typically operate on vanishingly small scales. Think individual atoms or subatomic particles collapsing under the noise of larger environments. Yet recent theoretical models suggest that under the frigid, sparse conditions of interstellar clouds, coherence could persist over micrometers or even millimeters. That might not sound impressive, but in molecular terms, it's like a crowd of people spread across a city, suddenly moving in perfect unison without communication. How? Through a quantum property called entanglement, where particles become linked so tightly that changes to one instantly influence the other, no matter how far apart they are. In the near absolute zero quiet of a molecular cloud, entangled molecules might have acted like a network of synchronized metronomes, their vibrations aligning to drive chemical reactions with uncanny efficiency. One striking example involves formaldehyde, a simple organic molecule ubiquitous in space. When chilled to just a few degrees above absolute zero, formaldehyde molecules can enter a state of quantum superposition, existing in multiple vibrational states simultaneously. Theoretical work published in Nature Chemistry proposes that in this state, clusters of formaldehyde could have collectively tuned their energy levels to match the frequencies needed to form sugars like ribose, a critical component of RNA. Instead of relying on random collisions, these molecules might have essentially self-organized into optimal configurations, leveraging quantum effects to bypass energy barriers that would stymie classical chemistry. It's as if the universe hacked its own rules, using coherence to fast-track complexity. But the real mind-bender is scalability. If coherence extended across even small regions of a cloud, it could have created pockets where reactions weren't just probabilistic but programmed. Imagine a dust grain coated in ice, its surface molecules quantum coordinated like a symphony orchestra. A single photon hitting one molecule might trigger a cascade of perfectly timed interactions, with entangled partners responding in lockstep to build chains or rings too intricate to assemble through chance alone. Astrobiologists call this quantum prebiotic chemistry, and while it remains speculative, lab experiments are starting to catch up. In 2020, a team at the University of Glasgow observed quantum coherence lasting microseconds in organic molecules at cryogenic temperatures, a fleeting glimpse of how life's ingredients might have danced to quantum rhythms billions of years ago. Critics highlight the fragility of coherence. Even in deep space, cosmic rays and thermal fluctuations should disrupt these delicate states, yet nature has workarounds. Some models suggest that the very ice mantles coating interstellar grains could act as quantum buffers, their crystalline structures shielding entangled molecules from decoherence. Others propose that coherence didn't need to last long, just long enough to bias reactions toward certain outcomes, like a loaded die subtly favoring life's winning numbers. Over eons, even a slight quantum nudge could have accumulated into profound chemical legacies. The implications rewrite the origins playbook. If quantum effects actively shaped prebiotic chemistry, then the leap from simple molecules to complex ones wasn't just a roll of the dice, it was a rigged game, with the universe itself tilting the odds. This theory doesn't just connect life to the stars, it binds us to the quantum undercurrents of reality, suggesting that the same phenomena powering quantum computers today might have crafted life's first molecules in the dark. yet mysteries linger. Could coherence explain why certain biomolecules, like the left-handed amino acids dominant in life, show such universal biases, or does it merely offer a new layer of complexity to an already enigmatic process? For now, the answers hover in superposition, both tantalizingly close and frustratingly out of reach, much like the quantum states that might have made our existence possible. What's certain is that the cosmos is far stranger than we imagined, and the line between physics and biology blurrier than ever, a reminder that sometimes the universe's greatest tricks hide not in the glare of stars, but in the quiet entanglement of molecules waiting to become something more. After 30 mind-bending theories about the universe's first complex molecules, we arrive at a startling realization: perhaps complexity wasn't forged through any single process, but emerged naturally from the interplay of countless simple rules. This is the profound insight of complex systems theory, where unremarkable components following basic physical laws spontaneously organize into intricate patterns far greater than the sum of their parts. Think of a murmuration of starlings. Each bird obeys only 3 simple rules: avoid collisions, align with neighbors, and stay close. Yet collectively, they create breathtaking aerial ballets that no single bird could plan or comprehend. The universe operates on similar principles. Take the Belousov-Zhabotinsky reaction, a chemical marvel where simple mixtures of malonic acid and bromate undergo rhythmic color changes, pulsing like a living heart without any external guidance. These oscillations arise from feedback loops, molecules inhibiting and accelerating each other's transformations in precise cycles. What begins as random molecular motion becomes a synchronized dance, proving that order can blossom from chaos when the right ingredients interact under the right conditions. Chaos theory reveals the hidden architecture beneath this apparent magic. The famous Lorentz attractor, a mathematical model of atmospheric convection, showed how deterministic systems could produce wildly unpredictable yet strangely patterned behavior. Tiny variations in initial conditions, the butterfly effect, don't always lead to disorder. Sometimes they funnel systems toward unexpected stability. In molecular terms, this means a slight fluctuation in temperature or pH near a hydrothermal vent might have nudged certain reactions toward self-reinforcing cycles, locking in pathways to complexity that would otherwise seem astronomically improbable. Modern research on autocatalytic networks drives this point home. When chemists simulate prebiotic conditions with simple molecules like formaldehyde and glycolaldehyde, they observe something extraordinary. These compounds don't just react randomly. They form interconnected webs where each product catalyzes the formation of another, creating self-sustaining loops reminiscent of metabolic pathways. The 2019 Formos 2.0 experiments demonstrated how such networks can selectively produce ribose RNase sugar backbone while filtering out less useful sugars, not by design but through the emergent logic of chemical kinetics. Astrobiologists see echoes of this process everywhere. Jupiter's Great Red Spot, a storm persisting for centuries, obeys the same principles of self-organization as a lipid membrane spontaneously forming vesicles in water. Both are examples of dissipative structures systems that maintain order by continuously exchanging energy with their environment. This isn't mere analogy, it's a universal playbook. From the swirling arms of galaxies to the branching fractals of lightning, nature repeats this theme. Simplicity begets complexity when energy flows through dynamic systems. What does this mean for life's origins? Perhaps the universe has a bias toward complexity woven into its fabric, a tendency for matter to arrange itself into ever more elaborate configurations when given enough time and the right constraints. The molecules that built us weren't forged in a single legendary crucible, but through the collective labor of countless ordinary interactions, each obeying unremarkable rules of physics and chemistry. In this light, life isn't a miracle against the odds, but an almost inevitable outcome of a cosmos built to explore every possible arrangement of its building blocks. As we close this cosmic detective story, remember, you're not just made of stardust, you're the universe's way of discovering what happens when simple particles follow simple rules for billions of years and suddenly find themselves wondering how they got here. The greatest theory of all may be that there's no single theory, just an endless cascade of emergent wonders, each more astonishing than the last. From ultraviolet starlight forging sugars in the depths of space to quantum vibrations synchronizing molecules across cosmic distances, the journey to uncover life's first ingredients has taken us through 30 extraordinary possibilities, each more surprising than the last. But here's the twist: the truth likely doesn't hinge on just one of these theories. Imagine the universe as a master chef, combining techniques from every recipe we've explored. Maybe amino acids brewed in hydrothermal vents hitched rides on comets, only to be concentrated by tidal pools and jump-started by volcanic lightning. Or perhaps interstellar dust delivered molecular blueprints that Earth's magnetic fields then refined into chiral perfection. The beauty lies in the interplay, a cosmic collaboration where chemistry's greatest hits converge to craft complexity. What's remarkable isn't just the diversity of ideas, but how many hold up under scrutiny. Lab experiments keep validating scenarios we once thought were science fiction, from shockwaves creating nucleobases to ice grains assembling RNA precursors. Nature, it seems, is less picky than we are ready to exploit every possible path, from the icy voids between stars to the scalding cracks in Earth's crust. This isn't a failure of science to pinpoint a single origin story. It's a celebration of the universe's relentless creativity. Life's building blocks might be less like a rare artifact and more like a universal language whispered in countless dialects across the cosmos. So which theory speaks to you? Do you envision life's spark igniting in the electric fury of a dust storm, or the patient rhythms of geothermal gradients? Maybe you're drawn to the elegance of quantum coherence or the brute force of asteroid impacts. There's no wrong answer, only a mosaic of plausibility waiting for the next breakthrough to rearrange its pieces. The comment section is your lab notebook. Share your favorite hypothesis or propose a hybrid we haven't considered yet. This conversation isn't just academic, it's a quest to understand our place in a universe that seems hardwired for complexity. And if this deep dive left you hungry for more cosmic mysteries, you're in luck. From the origins of dark matter to the enigma of rogue planets, the universe is brimming with puzzles begging to be unraveled. Hit subscribe so you don't miss our next adventure into the unknown, because the greatest story ever told is still being written, one mind-bending discovery at a time. Until then, keep looking up and wondering. The answers are out there, hidden in the stardust and the silence between the stars.